Right, in this video, we're going to talk about suggested homework problems from 4.2. I'm actually going to try to do this in two videos. In the first video, we're going to talk about summation notation, um, formulas for finding summations, and I'll even get up to, I think, finding lower and upper bound estimates of the area under a curve. But I will stop before I get to the limit definition of the finding the exact area under the curve, and I will save that for a second video. So let's start with number 5 and introduce the concept of summation. Most of you probably haven't seen this before, unless maybe you covered it in a pre-calculus class, or you've taken some kind of statistics class where you had summations. Usually statistics is the place that we see this. You may have seen the formula for the mean, that is the sum of the x values divided by n, and you might see x of I equals 1 to n in a very technical definition that you add up all of the different x's in your list from the first to the nth and divide it by the number of things in your list, which is n. We'll talk more about this index here, I, and how it gives us a lower and upper bound on the summation here. But just to draw your attention to that being something that you probably already have familiarity with in seeing the symbol. So it's a Greek letter sigma, capital letter sigma, as opposed to this lowercase sigma that you might have seen in statistics before. This is I equals 1 to 6 of 3i plus 2. And the capital S sigma is for summation. So we usually use a Greek letter that starts, that's the same letter, same sound as what the word is that stands in place of. So S, Greek letter S sigma for summation. So what this tells us to do is to take this 3i plus 2 and to evaluate it at, let's say that we call this f of I is equal to 3i plus 2. What we want to do is we want to take f of, this would tell us to take f of 1 plus f of 2 plus f of 3 plus f of 4 plus f of 5 plus f of 6. So I'm going to stick in 1, 3 plus 2 is 5. And then stick in 2, 6 plus 2 is 8. Stick in 3, 9 plus 2 is 11. Stick in 4, 12 plus 2 is 14. Stick in 5, 15 plus 2 is 17. Stick in 6 and I stop, 18 plus 2 is 20. You may notice that this is a linear equation with a slope of 3, so the increase each time in the sequence of terms here should be adding 3 because of this linear equation, that it has a constant rate of change. That might help you if you start off with the first one and add 3 until you get to the 6th term in the sequence. But we're finding a series, a summation of these terms. So notice that lots of times in these types of series that these things that I'm grouping together here will all add up to be the same number. They'll all add up to be 25 in this case. So I have 3 sets of 25. So my answer is 75. Now let's confirm this with the calculator. I have 2 different ways to do this. If I go into my list menu, go over to math, use the sum function, it's number 5, then go back into my list menu, go to operations, and use the sequence. And I have this set up already, 3x plus 2 with the variable x, starting with a lower limit of 1 and ending with an upper limit of 6 and stepping by ones. I can plug that into my summation there. So this sequence gives me all of these terms. Without the plus signs, the sum tells me to add up all of the terms. So I kind of mentioned that before about this idea of a sequence giving me this ordered list. The sequence would be 5, 8, 11, 14, 17, and 20. And the sum is going to turn it into a summation where it adds everything in the list. It gives me an answer of 75. Now, if I wanted to use sigma notation, I have to have a more advanced calculator, and it's in the math menu. If you have it, it's option 0 here, and you put in your index of x, start at 1, go up to your upper limit is 6, and then put in your expression in terms of x, 3x plus 2, and you get your answer of 75 as well. Try to confirm our answers when we can here with the calculator. So number 11 kind of goes the other way. We start off with the terms all written out, and we want to induce the pattern here. So 1 over 5 times 1 plus 1 over 5 times 2 plus 1 over 5 times 3 plus dot 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 plus 1 over 5 times 11 is going to be a summation since I'm adding all these terms together. 1 over 5i, I goes from 1 to 11. That's it. Let's move on now to the next problem. And before we talk about this problem, we have to talk about our 4 special formulas. I kind of mentioned this at the beginning, that there were going to be some formulas that we were going to talk about. These always start at I equals 1 and go to n, starting with a constant c. This would be the definition of multiplication, and it would be c times n. Formula 2, I equals 1 to n of our variable I here will be n times n plus 1 over 2. Summation from I equals 1 to n of our variable I squared is n times n plus 1 times 2n plus 1 over 6. And I equals 1 to n of I cubed is equal to n squared times n plus 1 squared over 2. This is the same thing as summation I equals 1 to n of I squared. I don't know if you noticed that, but it's that same formula there, just squared. So not a new formula, just square number 2 to get number 4. So memorize all of these, and you will need them throughout this this lesson, especially, and the next video here, and even throughout the rest of this chapter. You may come across them, but you'll definitely need to know them in this unit for your test. You almost certainly will have to find a lower sum and an upper sum, or even do a limit process to find an area, and you will need to know these formulas. All right, I think I've given you enough time to write all of those down. Start with number 17. Summation from I equals 1 to n, to n is getting replaced with 12 of 7. Since that's a constant, that will be 7 times 12 is 84. Let's confirm that with the calculator. Math 0, x 1 to 12 of 7 is 84. Let's move on now to number 21. 21 says I equals 1 to 20 of I minus 1 quantity squared is I equals 1 to 20 of I squared minus 2I plus 1. So that's going to be I equals 1 to 20 of I squared minus 2 summation I equals 1 to 20 of I plus summation I equals 1 to 20 of 1. So this is 20 times 21 times 41 over 6 minus 2 times 20 times 21 over 2 plus 20. This goes into there. And then this is 2 and 7, 1 and 10. 10 times 2, 87, minus 20 times 21 minus 1 is 2870 minus 20 times 20, 2870 minus 400 is 2470. And this is math 0 x 1 to 20 of the expression x minus 1 quantity squared. And 2470 is the correct answer. Let's look now at number 23. Summation I equals 1 to 7 of I times I plus 3 squared. I equals 1 to 7 of I times I squared plus 6I plus 9. Summation I equals 1 to 7 of I cubed plus 6I squared plus 9I. Summation I equals 1 to 7 of I cubed plus 6. Summation I equals 1 to 7 I squared plus 9. Summation I equals 1 to 7 of I is 7 times 8 times 15 over, this is 49 times 64 over 4 plus 6 times 7 times 8 times 15 over 6 plus 9 times 7 times 8 over 2. So 4 goes into 64 16 times, 6 comes out here, 2 goes into 8 4 times. We have 49 times 16 plus 7 times 8 times 15 plus 9 times 7 times 4. And I get 1876. Let's confirm that with the calculator here. X goes from 1 to 7 of x times x plus 3 quantity squared, and we get 1876. So now at number 25. Summation I equals 1 to n of 2i plus 1 over n squared. Well, the n's can pass through, and this becomes I equals 1 to n of 2i plus 1. So this is 1 over n squared times summation times 2 summation I equals 1 to n of I plus summation I equals 1 to n of 1. It's 1 over n squared times 2 times n plus 1 over 2 plus n. N can factor out. Uh, 2 comes out here, and this is n plus 1 plus 1 is 1 over n times n plus 2 is 1 plus 2 over n, and I'll call that f of n. So f of 10 is 1 plus 2 over 10 is 1 and 2/10. F of 100 is 1 and 2/100, or 1 and 2/100. F of 1000 is 1 and 2/1000. It's 1 and 2/1000. And f of 10,000 is 1 and 2/10,000, which is 1 and 2/10,000. So now at number 31. G of x is 2x squared minus x minus 1. We're given the interval of 2 to 5, and we're told to use 6 rectangles here. And we are to estimate the area finding the lower sum and the upper sum. Yes. So let's go ahead and use the calculator to help us here. Y equals 2x squared minus x. And I'm going to use my table setting to start at 2 and to increment by 0.5. And that's going to give me values of 2, 5, 2.5, 9, 3, 14, 3.5, 28, 20, 4, 27, 4.5, 35, and 5, 44. I could have done this with a sequence as well if I wanted to. In fact, I will go back and do this in just a second with a sequence. Now you'll notice that I have 7 things here, and I want to add the first 6, and I'll call that lowercase s, and I want to add the last 6, and I'll call that uppercase s. So I'm going to find the sum of the sequence of terms that are 2x squared minus x minus 1, the variable x starting at 2, going to 4.5, and increasing by 0.5. I'm going to type that into my calculator here. Second list, sum of second list sequence of 2x squared minus x minus 1, and variable x starting at 2, going to 4.5, and stepping by 0.5, and that lowercase s is going to be equal to, that's too big. I need to multiply that by the width of the rectangle now, which is 0.5, and I get 0.5 times 110 is 55. So this is going to be 0.5 times 0.5 times some sequence. All this stuff is the same, other than I'm going to make this from 2.5 to 5 by 0.5. So second entry, going to change this to 2.5 to 5, and then multiply that by 0.5, and I get big S is 74.5. And so my actual area is somewhere between this lower bound S and this capital and this upper bound capital S. It's somewhere between 55 and 74.5. That's the best that I can do right now, is to just give you bounds and say that it's somewhere in there. Let's look now at number 35. And we're going to be using left endpoints and right endpoints here to find S and lowercase s and capital S for 35. So left endpoints for lowercase s, we use 1 for our width, and we have 1 plus left endpoint is 3. Left endpoint is 1, 2, 3, 4. Left endpoint is 1, 2, 3, 4 and a half, it looks like. And we'll add that together because we want n to be equal to 4 here. So this is 4, 8, 12.5 for lowercase s. And our capital S is 1 times, and we'll start with our right endpoints. So this will be 3 plus 4 plus 4.5. And we'll get a right endpoint over here of 1, 2, 3, 4, 5. So this is 7, 11.5, 16.5. And our actual area will be somewhere between 12.5 and 16.5. All right, let's look at 43. And 43 is going to be my last one for this first video. We have f of x is equal to 5x squared on the interval 0 to 1. And we want to find the estimate using the using n rectangles and using our left and right endpoints for estimates. So our left endpoints will be notated by lowercase m sub I, and the formula for that is given by I minus 1 times delta x. So that's going to be delta x is 1 minus 0 over n is 1 over n. So this will be I minus 1 times 1 over n. My right endpoints will be notated by capital M sub I, and they'll just be I delta x. And so that will be I times 1 over n. It's going to be easier to calculate the upper sum with the right endpoints than the lower sum with the left endpoints. But let's go ahead and do the hard part first. Lowercase s is summation from I equals 1 to n f of lowercase m sub I times delta x, summation from I equals 1 to n of 5, big bracket, I minus 1 times I over n quantity squared, because it's 5x squared, times a delta x of 1 over n. So that will be summation. Actually, let's pull some stuff out here. Let's pull the 5 out, and let's pull the 1 over n's out because they can pass through. They're not i's. So 1 over n squared times 1 over n is 1 over n cubed. Summation I equals 1 to n of I minus 1 quantity squared. So 5 over n cubed, summation I equals 1 to n of I squared minus 2i plus 1. That's 5 over n cubed times n plus 1 times 2n plus 1 over 6 minus 2n times n plus 1 over 2 plus n. 2 over 2 will cancel. And that leaves me with 5 over n cubed times, let's pull the common factor of n out of all these, n plus 1, 2n plus 1 over 6 minus 20n plus 1 plus 1. So n will cancel here, and with 5 over n squared times 2n squared plus 3n plus 1 minus n minus 1 plus 1. This is over 6. So let's make a common denominator here of 6. 5 over n squared, 2n squared plus 3n plus 1 minus 6n over 6 is 5 over n squared times 2n squared minus 3n plus 1 over 6 is 5 over 6 times 2 minus 3 over n plus 1 over n squared is equal to 5/3 minus 5 over 2n plus 5 over 6n squared. And that is my lowercase s. My uppercase s is going to be the summation from I equals 1 to n of f of capital M sub I delta x is equal to summation I equals 1 to n of 5 times I 1 over n quantity squared 1 over n. It's just like before. I'm going to say that this is 5 over n cubed summation I equals 1 to n of I squared is equal to 5 over n cubed times n times n plus 1 times 2n plus 1 over 6. N cancels out, makes this 5 over 6 times 2n squared plus 3n plus 1 over n squared is 5, 6 times 2 plus 3 over n plus 1 over n squared is going to be 5/3 plus 5 over 2n plus 5 over 6n squared. Again, this is our capital S. So we're somewhere between those things. The actual value of A is somewhere between 5/3 minus 5 over 2n plus 5 over 6n squared, and 5/3 plus 5 over 2n plus 5 over 6n squared. All right, I'm going to wrap it up right there. Even though I could probably do the whole thing in one video, you probably would like a break after all that, and probably would like a separate video to come back and talk about the limit definition of this here. The idea, though, as n increases, our estimates for our area get better and better. We can squeeze in using a limit process as n goes to infinity, and we'll squeeze out all the air. As n goes to infinity, we get infinitely many rectangles of this idea we're going to call an infinitesimal width. An infinitesimal is like infinity, but the opposite idea. It's really, really tiny, almost zero. Instead of infinity is really, really big. So the idea of the infinitesimal is going to be really important here for this idea of anti-differentiation and integration. And one of the ways in which we're going to use integration is to find the area under the curve. We're going to build to the limit definition of the definite integral. Don't worry what all that means, but just think of how you did limit definition of the derivative in the beginning sections here of calculus, and how you built towards knowing some formulas that would always work all the time. Well, we're basically going to do the same type of thing. We'll start with a limit process. We've already learned some basic formulas in the last section, but we'll learn how to use those techniques along with the limit process here to come up with the answer for finding the area under a curve for any of those basic formulas that are nice. When it's not nice, when it's not one of those formulas that we already talked about in 4.1, then we're kind of stuck with this limit process that we're going to talk about next time. So it's our fallback position when we don't have one of those elementary functions. All right, that's it for this video. We'll come back next time and finish up our discussion of 4.2 with the limit process to find the exact area under a curve. See you for the next video.